Hey everybody, my name is Anish, and I'm excited to tell you about some of our recent work on a new approach for verifying constant time crypto. So suppose you want to build a really secure system. Well, a great way to do that is to use dedicated hardware. Run your sensitive code on there, keep your sensitive data on there. The simple hardware can have really simple processors. You can use simple software on there, run your crypto code on there without having to time share, have any interruption or anything like that. And so this approach eliminates many side channels by design. So that's awesome. But one challenge that remains is the end-to-end timing behavior of the hardware, which could still leak secrets if it's not managed carefully. Now, the state of the art for dealing with timing side channels and gaining confidence that your code doesn't suffer from these timing side channels is to use something called leakage models. You can prove that leakage is independent of secrets. And this is a standard approach. Lots of verified cryptography does this, and it's great. We have software that we have a lot of confidence in that it's constant time. But there's some downsides to this approach. One issue is that there can be a gap between the leakage model and how the hardware actually behaves. And this can go in both ways. You can miss certain leakage in the leakage model. After all, it's an assumption about how hardware behaves. And on the other side, your leakage model might be too conservative. So you might have code that's reasonable, but the leakage model prohibits it. Also, a lot of these verified cryptography projects do analysis in a high-level language like C. And so that means that you can't really reason about code that needs to do things like access control registers or talk to peripherals or things like that. That's just below the level of the language you're working with. And also, this requires trusting compilers to preserve constant time behavior. So we have an alternative approach that I think eliminates a lot of these downsides. So our plan is to cut out the middleman and do something wild, which is verifying the timing behavior of software directly against a particular hardware implementation. What we want to do is that we want to prove that a particular hardware implementation, and here we're really talking about like cycle level model, we have the RTL. We want to prove that that runs a particular hardware program, a particular binary, in constant time. And then here we're talking about this really fundamental notion of time, or as close as we can get to it, which is, in our case, cycles. We're going to prove that this hardware runs this program in a constant number of cycles for all inputs. That's the plan. And to do this, we built a tool that can verify this property. And so far, we have some experiments that show that this could be a promising approach. We've applied it to a couple different processors, a couple different programs. So one way to understand what we're doing is to compare it to software testing. What you can do today with standard tools as a standard approach is to take some hardware, like take the RTL for a processor, and you can run it on top of a simulator, right? And you can not only simulate the hardware, you can load some software into that hardware. Like you can do something like compile the Linux kernel and get your hardware to boot up Linux, and do that all in an RTL simulator. So if we want to use this basic setup for reasoning about timing behavior, you could do a pretty classic testing or fuzzing sort of approach. Just run your software on some concrete data and see what happens. See how many cycles it takes for it to finish executing. And if you wanted to gain more confidence, you could try this a bunch of times with different input values, right? But you can't really exhaustively test all possible inputs in this setup. That would take forever. It's intractable. And so our approach, or our plan, is to effectively do this, but prove this property for all inputs. And the way we do that is by replacing the RTL simulator with a symbolic RTL simulator. The fundamental part of this approach is using symbolic execution. And this way we can actually prove that this property holds, this constant time execution, over all possible inputs. So at the core of this is a symbolic RTL simulator. What we do is we compile Verilog code to Rosette code. So Rosette is this awesome solver-aided programming language that runs on top of Racket. And basically the abstraction it provides is you can write something that looks roughly like normal Racket code, and Rosette lifts it to operate on symbolic values. And so by translating the circuit to Rosette, we can basically get cycle-level circuit simulation, which works not only with concrete values, but also with symbolic values. And we can walk through an example to see what this looks like. So here's some really simple Verilog shown on the left. This is an implementation of a counter. What it does is when the enable line is asserted, the count is incremented by 1. So we pass this through our toolchain, and we get some Rosette code. It gives us a state machine representation. So the interesting part here is this step function, which says what happens to our circuit state after one cycle of execution. And then with this, we can do things like you can do with the standard RTL simulator. So we can instantiate a concrete state. We can say, okay, let's assert enable and step by a cycle. Okay, the counter is now 1. But the cool thing is we can also do this with symbolic values. So we can say, let's instantiate a symbolic circuit. And here this counter $41 is this symbolic variable. And we can say, okay, what happens when we step this thing with a symbolic input value? And we can see here that we get this if-then-else expression that captures this fact that if the enable line is asserted, the count is incremented by 1, otherwise it stays the same. So this is applied to a really simple example here, but we can scale this up. We can also do some interesting things like mixing concrete and symbolic state. So here on the right, I have a kind of simplified version of the state of a whole processor now, or whole system on a chip. And a lot of this is symbolic, but a part of it is concrete. One thing we can do is we can take a program, compile it into a binary, and stick it into the ROM here. And then we can symbolically evaluate this whole circuit. And it's important to understand here, like when we run this thing, we're not symbolically evaluating the code that we're intending to run on top of the hardware. We're symbolically evaluating the hardware itself. Like we're calling the step function again and again. We do step, 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 and that will, in this case, since we have a processor, it will make the process, we have fetch instructions for memory and do things with the code that's in there. And to go from the symbolic RTL simulation to doing this timing verification, we don't really need to do all that much more. What we can do is we can mark the input data as symbolic and then run our symbolic simulator and just count the number of cycles it takes for the thing to finish. We can check that this completion time is independent of symbolic variables, and that proves the property we're looking to prove. And that's actually all we need for some of these basic examples. So we've taken, for example, some off-the-shelf ED25519 code. I went on GitHub, found a GitHub repo that implements ED25519 in C, and compiled it to run on this really simple processor. So there's this Pico RV32 processor, which is a tiny RISC-V processor. And then we just stick it into our tool, and it says, okay, like no matter what your secret key is, it takes exactly this many cycles to finish signing it. So let's take a step back now that I've explained the basic approach and see how this approach addresses some of the limitations of leakage models that I talked about earlier. So doing this, we get really precise analysis. We have high confidence in non-leakage because we're not making assumptions about hardware. We're just proving directly against hardware. There's no formality gap here. And it's also not too conservative. So instead of verifying this proxy, like instead of verifying against this leakage model and saying we have no leakage, that means our end-to-end timing behavior is what we want, we just prove the timing behavior directly. We can reason about any code, just compile it into a binary. That code can do whatever it likes, including interacting with fancy hardware features that our hardware supports. Though the approach does have some limitations. So far, we've only verified some pretty simple processors, and I'll talk more about exactly what we've done so far in a moment. We also need to repeat verification for every single hardware target. So this is like a totally non-modular approach, right? And this is why we're trying to make this as automated as possible. And finally, what we're doing is we're verifying the end-to-end timing behavior of programs. And currently, we don't really have a plan for saying anything about fragments of programs. So we can't, for example, verify a library function and later use it and have some guarantees about how it'll behave. It's really like the entire program. We're reasoning about main.c. So to evaluate the approach, we did some case studies. Still early work, so we have some small examples so far. I talked about this Pico RV32 one already. We've also tried this with slightly fancier processors. So there's this open source RISC-V processor called the BiRISC-V. So to give you some sense of how much complexity is there, it's a dual issue, 6-stage pipeline processor, slightly fancier than our initial example. And on that one too, we can run the software, we can prove exactly how many cycles it takes to execute, regardless of secret keys. And in this particular case, we've set up our tool to take some extra proof input from the proof developer and we need some annotations to have good performance there. And we've also applied this to not just like standard processors, but cryptographic accelerators as well. So there's this neat device called the OpenTitan, developed by Google, and there's this cryptographic accelerator in there called the OTBN. So that runs a custom ISA, and we've proven some software on top of that as well. And let's look at another example. I think this is kind of cool to look at. We can show that our analysis is not overly conservative. So here on the left, we have some code that branches on a secret. And this is a big no-no in constant time cryptography, right? Like if you wanted to do crypto or parsing or something, you just cannot have code that looks like this, because the leakage model will say, like, as soon as you get to your if secret, like you have leaked the secret. But when we're directly verifying end-to-end timing behavior, this is not inherently bad. As long as we can show that this code executes in constant time regardless of the secret value, that's totally fine, right? And so this particular example here, which has carefully written, kind of wacky-looking assembly code in each branch, we've shown that this runs in constant time on a particular processor target. And it's really targeted toward this particular processor. So if we switch processors, it actually no longer runs in constant time. You need to tweak the assembly code in each branch to make that the case. Yeah, so we can show that we can support this really precise analysis. Now, taking a step back, it might seem surprising that this approach works at all. Like, how can we symbolically execute hardware for millions of cycles, right? And the main reason this works is we're able to minimize branching, minimize symbolic branching. The particular problem we're trying to solve is proving that code runs in constant time. And so the code is already written in a way that's intended to run in constant time, right? Like if it's correct, it's not doing lots of branching on secrets. And we also benefit from just how hardware is designed. There's this natural separation between the control and data path in hardware. And so conceptually, when we're symbolically executing a program on symbolic data, what's going on at the hardware level is that the control part of the hardware state stays concrete, while the data path can be symbolic. And so this means that when we symbolically evaluate step, step, step again and again, it doesn't blow up because the control can stay concrete. And we also benefit from the underlying Rosette library that does some smart things to optimize symbolic evaluation. And there are some cases when symbolic evaluation doesn't just work. It's not like this works for free on all fancy hardware. And so we have some support for letting the proof developer give some extra annotations in order to help minimize symbolic evaluation, like both symbolic evaluation and branching. So that's our approach for verifying constant time code, very different from leakage models. And if you're interested, I've put all the code and docs and some examples online, so you can go to that link and play with it.